So today I'll show you how to import the climate data that's included with VTAS version 3.2. First, I downloaded the zip file that contains the VTAS executable input files and supported files. It's in this distrib folder here. So if we double click on it, you can see we have a number of input files. We have the VTAS executable, we have the manual, then we have the supported files here. Here we're interested in weather data. If we click on weather data, you can see that inside we have a number of these Microsoft Excel comma-separated values files, and they're fairly decent size. They're about 1.8 megabytes or so, and there's a whole lot of them. There's a large number of them. So these files contain all of the climate data for a wide number of locations. Unfortunately, these locations are not readily listed here. You have to click inside the file. So for example, if we double click on the first one and open it up in Excel, it's listed here on the cell B1. You can see that this is for 29 Palms, California. So if you look here, there's a large amount of data here. But we're really only concerned with a couple of things. We're concerned with the dry bulb temperature as well as the relative humidity. Also, if you look at this data, the data is provided from January 1st all the way to December 31st. So you can see that there's daily, and if you look even further, there's hourly data for every hour of a given year. So this is what we use for our climate data. Now, rather, of course, than have you open this up and figure out how to import the data yourself, VTAS has it done automatically in a fairly simple manner. Let's first open up a command window. And we'll go to our distrib folder, and we'll run VTAS. We can choose here to open an existing file, just for the purposes of showing the demonstration here. We'll open up input1.txt. And we'll go through our standard screens for a while that contain all the values that's been read in from the input deck. So once we get to the external properties screen, we have the option here to read it from the weather data file, which we'll choose. And notice that when you click on that, everything else is grayed out because we're no longer specifying the external air dry bulb temperature or the humidity. Click on Next, and a new screen comes up, which is the Read Weather Data screen. First, we choose the state that we want, and this contains a database of all the states that contain at least one location in the weather data directory. So let's choose Louisiana, just for fun. Then notice now when you open the state, then now the city becomes highlighted, and you can choose any of these locations within the state of Louisiana. If you want to choose a different state, Mississippi, you can see you have different locations within that state as well. So then you have the choice of choosing a simulation. Either you can run it at the worst case conditions. In our case here, we call it the worst case in that when the data is imported for a given location, then VTAS calculates the highest external enthalpy that is seen in all the hourly weather data listed for an entire year. That worst case scenario then is used to design the cooling equipment to make sure that it can handle the heat loads for those given external conditions. There's also the ability to design at the worst case conditions, but then we can put in a frequency. And here the frequency that we'll use is 2. What this does is it consolidates by phase averaging all of the hourly data into 2 equivalent days, one for the first half of the year and one for the second half of the year. And you can obviously have a number in this box between 1 and 365. If you do 365, it'll essentially model every hour of every day of the year. And if you do 1, it consolidates everything into one equivalent 24-hour day. So here we'll use 2. And we'll leave everything else as it is. Here's our system setup. So if we click on Continue and we click on Go, you can see what it's doing now is it's importing the weather data for the specific location here. Now this takes up to a minute or so because there's a lot of data in that file that needs to be imported, and that maximum external enthalpy needs to be calculated. Now as you can see, as it's doing the run, it has 49 data points that it's running. Again, we're simulating 2 equivalent days, and therefore there's 48 hours in the 2 days. And then run 49 is that worst case scenario that's used to design the equipment. Notice that the reason why these days are being simulated so quickly is because the maximum time required by a VTAS is to do the fluid flow calculations. So they're done one time, and then after that, only the heat exchange calculations are done much faster. So here's our design solution here. So this is our worst case solution here, and you can see that it just looks like any other steady state output screen from VTAS. You can see where the heat transfer is, which is maximum in the cooling tower, and the extra destruction is maximized in the chiller. If we go back to our strip folder here, we can look at our outp file, which provides our output parameters. And in this, there's a couple of small changes than what we've normally seen. Now you can see there's an annualized POE and an annualized WE. So this is based off of our phase averaged equivalent 2 days of the year. The extra destruction is provided in watts, but also the annual average in kilowatt hours is provided. So the wattage here is the average of 48 runs that represent the 2 equivalent days. And then this has been converted into kilowatt hours over here on the right. And finally at the bottom, these minimum design requirements are applied for that worst case scenario where it has the maximum external enthalpy.